Hello everyone, this is the first of two videos on chapter 17. This video we're going to go over just basics of superposition of waves and talking about standing waves on strings. Next video we'll apply this to sound waves, talk about standing waves for musical instruments and talk about beats. Later, there are parts of this chapter that we're going to skip over for now. So interference of waves, constructive versus destructive interference. We're going to revisit this chapter in preparation for talking about this in the context of light. So there will only be two videos for this chapter. The problem that we want to look at, that we want to be able to address here, so I drew a picture here of someone with a rope, and I drew a single wave pulse right here. So notice how the wave, so the person flicked up and then down. So the wave went up first and then down right here. So they flicked it up and then down, and this wave pulse is traveling towards a wall. And we want to be able to describe what happens as this pulse is going to be reflected from the wall. So it's going to address what goes on, we need to know what happens when the pulse is reflected, and we need to know what waves do when they're on top of each other. All right. So your book spends the whole first section just emphasizing that waves operate a little bit differently from particles. So the idea of superposition, and you use this in physics 2B when you talked about superposition of electric field. So if you remember from E&M, if you were to calculate like the electric field, the total electric field, you would find electric field from different sources and then just add them together. So you could so if you had like if you had a plus charge here and a plus charge here and you wanted to find the electric field right here, you could just pretend, you could just cover up one of them, find the electric field from one of them, find the electric field from the other one, and then just add them together. Just pretend that the other one didn't exist and just add them together. So for superposition, you can just think of this as like, you can add things together and not worry about them interacting with each other. Like the electric field doesn't interact with another contribution to the electric field. You can just add them all separately. So the same thing is going to happen with waves here. So to give you an indication, suppose we had two wave pulses that had a positive displacement of rope from equilibrium. One's traveling to the right, one's traveling to the left. What happens when they start getting on top of each other? Well, they just are going to add on top. So really I have to think about, so the amplitude is going to get a little bigger here. It's maybe difficult to draw. It's symmetric. So it'll start to look something like this. So really what this is two waves on top of each other. So there's still one traveling to the left and one traveling to the right, but they're starting to overlap. And where they overlap, we can just add the displacements together. So there's a point where the peaks overlap where it just looks like one hump. So if we took a picture at that one moment in time, it would just look like a single hump. And then so when we wait a little bit longer, it just looks like the two wave pulses have passed through each other unaffected. So your book makes the point that this is very different from, it says unlike particles. See how so figure 17.1, unlike particles, two waves can pass directly through each other. So you would not at all expect two balls to just pass through each other and not talk to each other. But that is what happens with waves. And it's surprising because it's still particles that are moving, particles that comprise the rope. But the overall effect is for them to just pass through each other. So sound waves behave like this. They'll just pass through each other. So it's hard to bounce. You know, if you're Bill and you're trying to prevent Alan from hearing speaker B, you can't really throw something in the way, right? You can't throw a sound wave to deflect that sound wave reaching Alan, right? That'd be weird to think about. So you can start to get a little mathy here. So this is a more quantitative example that your book goes over, just to describe that really you can take any one point and just add up the two displacements and really just add those two numbers together to get the overall wave pulse at any moment in time. It gives you the chance to practice this with this example. So if we were to look at, so what is this? This is Stop to Think 17.1. So let's see, stop to think. Stop, think. 17.1. So it gives us these two wave pulses, and it says what happens after 6 seconds. So this picture is t equals 0. This picture on our left is t equals 0. What happens after 6 seconds? The way to think about this is to draw the two wave pulses separately. Where would they be? Just draw them out separately and then add the two together. So let's look at the one on the left. The one on the left, it starts off at 1 and ends at 6. So after 6 seconds, it's going to go all the way to 7 and end up at 12. 8, 9, 10, 11, and 12. Right, so the one, so x equals 1, we'll move over 6 spots to the right and go to 7. So that'll go right here. So it looks like this pulse goes up pretty quickly, and then it gradually dies off by the time it goes to 12. This is testing my word skills. Okay, now let's look at the second pulse, the one on the right there. It's going to move over to the left by 6 meters, right? 1 meter per second, and then we're looking at 6 seconds later. So the 14 is going to go over to 8. So it looks like it's going to end right here at 8. And then the 19 is going to go over to 13. So we'll go over here. But this wave pulse, it looks like it goes up quickly on this side, and then it gradually drops off on this side. So the net result is going to be the sum of these two. So nothing interesting happens until 7, nothing interesting happens, this is 12, 13, and 7, and 8. Nothing interesting happens after 13. So it looks like all of our answer choices satisfy that. They all go between, they're all non-zero between 7 and 13. Just this one really jumps out because they definitely don't destructively interfere at 10, right? So if we look at 9, looks like 10 is right in the middle here. At 10, it's a non-zero value for both of these. They're both positive, and we add them together, it's still going to be positive. So we definitely know A is not going to be the answer. And actually, if you maybe assign values, you really just need to use the fact that that these lines are linear. Lines are lines. They gradually go from 0 to their maximum value. Halfway in between, they're at half the maximum value, and there's 2 of them right here. So when we add those two together, it's going to be the same value as the maximum right here. And you can look at any point in between, and it'll actually be just the same constant value. So it looks like the answer would be C here. Okay, so you just consider the wave pulses separately and add them together on top of each other. So this was a special, t equals 6 is the special moment where it's flat right there. In general, it doesn't look flat. But if you happen to take a picture at that moment in time, it would look flat. The overall pulse would look flat. Okay, so now we want to get into standing waves. And at this point, just so you have an idea of what we want to be able to describe, I would maybe pause the video and look at the link that I have in the description for what a standing wave looks like. What's interesting about a standing wave is that it's a result of waves that are moving to the left and right, but it just looks like, if you're watching a video of a standing wave, it just looks like the rope is moving up and down. You can't see any side-to-side motion. It's not at all obvious that there is any side-to-side motion. We want to understand why that is. All right. So before we get into standing waves, I want to mention one fact first. So that fact is that if you have a wave pulse traveling towards a wall, this is a fixed wall with a fixed So the rope is tied to the wall right there. So this spot can't move. So the rope is tied to the wall right there. What happens when the pulse starts to arrive at the wall? Well, this knot, whatever's tying the rope right here is going to pull down on the pulse. So overall, the pulse is going to feel a force downwards. And what winds up happening to conserve the energy here, the pulse actually is going to look exactly the same, but because of that overall downward force from the wall, when the pulse leaves, it's going to be inverted. So the pulse after it bounces off the wall is going to be, if the initial displacement was positive, it's going to be negative afterward. Okay, so it inverts. So this depends on how. So this is a result of that support here being stationary. If there's a way of tying it to, say, a bar, and just so you had a ring tied to a bar right here, and the ring was allowed to go up and down, then it wouldn't invert. The ring would kind of come along for the ride, and then the pulse would bounce off with the same sign displacement. Okay, so I think we're ready to. So to explain standing waves, we actually want to address this problem right here. So let's go back to the person with the rope and the wall. So remember, this wave pulse is traveling toward the wall. So I want you to think about what happens when this pulse, the positive pulse, bounces off the wall. So remember, point P is going to arrive at the wall. So at that moment, when point P gets to the wall, this pulse, circled in black, has already inverted. So that pulse, when it inverts, it's going to overlap with this, right? It's going to be a negative displacement on top of the other one. So maybe back to, what color was that, green? This is where my color blindness is messing with me. So back to the original problem. Back to the original problem. To problem at the beginning. So what happens is that, so I'm going to do this trick where I'm going to use a dotted line to talk about the two pieces of the overall wave pulse. So we had the wall. We had, I think I was describing point P in teal right here. So we're looking at the moment when the point P arrives at the wall. So at this moment in time, we have, so there's the rope here, and there's two different pulses. So now there's, there was this piece that's still traveling to the right, and there's another piece. So remember, the positive part has already reflected off the wall, and upon that reflection, it underwent a inversion. So it's on the negative side. So when we add these two pulses together, the overall wave pulse is going to be bigger in amplitude and negative. So this wave right here, I'm hesitant to, I should describe. So remember, there were two ingredients that went into this black line. One of them is a pulse that's traveling to the right, and one of them is a pulse traveling to the left. So I'm hesitant to say, I can't say that this is just to the left or to the right. This is really a sum of two pieces that are traveling to the left or to the right. So if we were to take a snapshot, as this wave is halfway down, half of it has bounced off, half of it's still going towards, it's going to be negative and bigger in amplitude than the wave pulse originally. So then if we wait until the other half of the wave has reflected as well, it's going to look something like this. This half of it is still moving along to the left right there, and then half of it's moving along, and then this piece, the negative side will invert again, the second half of the wave will invert and become positive. So now this whole wave pulse will be traveling to the left. So now point P has already bounced off, and it's, this whole thing is now traveling to the right. So this is in the middle of the pulse bouncing off the wall, and this is right after. So in the middle of the pulse bouncing off the wall, the two will constructively interfere. The two halves, the two pieces, the two humps of the wave pulse will interfere with each other constructively. to get this big wave pulse, and then after it goes back to its normal magnitude, right? You've separated the two pieces now. So why is this relevant for standing waves? Well, standing wave, so I want you to consider what happens if there's a wall right here and there's a wall right here. Okay, and imagine you had two pulses. So let's look at this. So one of them is traveling to the right. So I have one color there, and then another color. Imagine this one is right on top of it, but it's traveling to the left. Okay, so what happens when, so each of these has a peak right here. What happens by the time that peak bounces off and gets right here? Well, both of these are going to invert, right? Whether the red one is traveling to the left, or I think this is purple, traveling to the right, they're both going to invert, and they're both going to wind up down here by the time that happens. So you'll have to take the wave speed and figure out how long it takes for this to get back to here. But both of them are going to go here. Both will be on the bottom. So what happens? So as these keep bouncing back and forth, they keep overlapping constructively. So when they're either both on top or both on the bottom. When they're halfway, when they're in the process of reflecting, so like when this maximum reaches the wall, then they're going to destructively interfere, and the pulse will actually look like this. They'll add together to be 0. So really, the wave, the overall what happens over time is that this is what the string would look like. So any one point on the wave, this will bounce back and forth between these 2 points. It'll start up here, go to the middle, go to this negative amplitude, go back to 0, back up. This one will go back and forth over a bigger distance. And right here, this only goes from here to here. The key point to take away from this is that standing waves come from 2 traveling waves going in opposite directions. Traveling waves in opposite directions. So your book talks about this mathematically in this next section. So they actually look at 2 waves of the same amplitude and same frequency traveling in opposite directions. So there's 1 plus and one minus here. And they just go through some math of adding the 2 together. And they overall see that they can write this. We're all same team here. We can write, so there's a function, there's x, so we'll call this x equals 0 right here. There's x, and then there's the moment in time. So we can still talk about the displacement of any piece of this rope. So it matters where we are, and it matters what time we're looking at. So we can write it as a sum of 2 sine waves, one moving or 2 traveling waves, one moving to the right and to the left. But the math simplifies so that it's some amplitude times cosine omega t. So notice how this is different than what we've been writing. What we've been writing is kx plus or minus omega t. But what happens is that this totally separates out the amplitude from the oscillatory motion. So notice how any one of these particles is just doing oscillatory motion. That's the cosine omega t, but the amplitude depends on where we are. So this a of x depends on where exactly we are. And a of x is equal to whatever the maximum amplitude is. So this big A would be like this right here. Big A times sine of kx. And k is only allowed certain values. So the reason this looks so nice is that everything perfectly overlapped with each other. Right? So we start off with 2 waves that were, nice, and they were both positive and overlapping with each other right here. And they'll stay that way and produce this standing wave. And that's tied to the fact that we had 2 nodes at the end right here. So as long as you have nodes at the end, which restricts the wavelengths, the allowed wavelengths, so k can only take on certain values. K can only to produce a nice standing wave pattern like this. K can only be the values can only take on certain values. So remember, K is related to wavelength. And right here, it's easy to just visualize the wavelength. So it looks like this is a half wave right here. So if I continue on this wave right here, maybe I should do this in black. So remember, the wave only exists between the two walls, but I'm just going to continue on and think about, so this maximum and then continue right here. It looks like the wavelength right here is equal to 2 times the length, the distance here between the two walls. So if that's L, the wavelength of this standing wave is 2L. And really you can fit any any wave, any standing wave could exist on here as long as you have nodes at the two ends. Okay, so what standing waves are possible? And that's where you're, oh, by the way, there's a factor of 2 right here, where I didn't write that factor of 2 because the lowercase a in your book is talking about the amplitude of a single wave. And then when you add the two together, the two amplitudes can add, so the 2 times lowercase a is what I'm calling capital A right here. So your book gets into, so it's talking about the allowed values of K right here in general, but they really want to focus on standing waves on the string, so that they finally talk about the reflection, why this occurs. They give an overall formula, so I'm getting towards where that formula is coming from, but I want to talk about it visually here. What standing waves are possible? So if you have the two walls, you can have, so the main one that would exist is right here. So this is called the fundamental frequency. So other ones could fit in there too, though, right? You can also have. So by the way, we're representing the standing wave with just its maximum right here, right? So really, the standing wave is doing this. It's going up, down, up, down, up, down. But we're just representing that whole thing with just the amplitude. So it's understood that this is going to be bouncing down and up. So continuing this on, we can have other ones. So this one is the biggest wavelength that we can fit in there. The next one is we can have a node right there in addition to at the end. Remember, we need nodes at the ends as well. Another one is this one. So we put 2 nodes in there and then have another node right here. Okay, so we can label these, so we call this, so your book uses the letter M to describe these standing waves. So this is M equals 1, M equals 2, M equals 3. And in general, for waves on strings, you can think of M as the number of antinodes. So an antinode is this location where you get the maximum possible amplitude. So the things in solid lines, these are called nodes. So these remain stationary. These are points along the wave where it's not moving. So see how for M equals 2, if we wait a half a period, this hump is going to go on the opposite side, is going to go on the bottom side, and the lower one is going on the top. But this point right here isn't moving over time. It's stationary. These are, you can think of these as stationary points along the wave. Antinodes are where they're doing the maximum possible displacement. So here is an antinode. And M is equal to the number of antinodes. Now you got to be a little careful. So with this definition, this statement is only true for waves on strings. So this is not going to be true when we talk about musical waves. Only for this section for waves on strings. But see how there's 1 antinode for M equals 1. There's 2 for M equals 2. There's 1, 2, 3 for M equals 3. So that's a nice way of getting the M value. Now you can draw pictures and just note that for m equals 1, it looks like the wavelength is 2 lambda. For m equals 2, this is a special one where, see how one whole lambda is exactly equal to the length of the between the two walls here, between the two endpoints. So this one has lambda equals L. The general formula here is the lambda for the mth mode. So the wavelength depends on which mode we're talking about. It's equal to 2L over m. But really, you should be able to just draw any of these standing waves and be able to derive the lambda based on how many waves fit in between those two endpoints. Okay, so you might want to take a look at this formula. This problem. So pause it and read it right now. The key piece of information in the problem statement is that they tell you that m equals 3. So when they tell you m equals 3, you know the wavelength. You know how the wavelength relates to the length of the string. So then it's just combining that with some facts that we had from last chapter about wave speed and how that relates to tension and linear mass density. That's how you would approach this problem. The rest of the section is just saying that these ideas are important for standing E and M waves. For example, your microwave is producing standing E and M waves, and applications with lasers too. They leave that as an example. Okay, we'll talk about standing waves with sound next time.